Hi, my name is Zhen Tong. I'm from University of Notre. This is my poster. So my work today, I'm presenting is prototyping a virtual full duplex with a rapid on-off division duplex. So as you may know that current days, all the radios are half duplex radios, means they either do time division or frequency division duplex. But people started to look at full duplex radios because if you can do the transmission at the same time on the same frequency bandwidth, you can actually double the throughput theoretically. So that's very attractive. So what people are now doing is they try to use new hardware circuits to do the self-interference cancellation. So because when you try to transmit and receive at the same time, you have a very strong self-interference. So different groups are working on different approaches. For example, Stanford, Rice, and NEC labs, they basically have very similar ideas. They try to use a new circuit to do the self-interference cancellation. Here in our group, we try to do it differently. We propose a new duplexing scheme. So the key idea here is we try to introduce the on and off slot in one transmission frame. So basically, for a traditional frame, we try to divide a long frame into small pieces, and we each node try to transmit according to a random on-off signature. So when the signature is on, we try to transmit a small piece. When the signature is off, we try to be in quiet so we can receive from the other node. So overall, we can actually achieve a virtual full duplex in the frame level. So that's the main idea here. So the application for our scheme can be, for example, continuously cognate radio. For example, if the secondary user try to transmit using our scheme, we can easily detect the primary user transmission in a very quick way. For example, since the off slot, we can sense the channel and see the transmission, then stop the secondary transmission immediately. So the main application focuses on the delay-sensitive scenarios. So the main work is try to implement this duplexing scheme on hardware. We want to see if it works in practice. So this is our architecture. So basically, we have similar. We based on our implementation on wireless LAN technology, but since the frame is kind of different, it's the on-off transmission. So we have a special on-off assignment for the transmission. We also have channel coding, channel encoder-decoder specially designed for our algorithm. So this is our platform. We're using USRP LabVIEW platform. We try to implement a point-to-point communication first, and so this is a main implementation. So this is a frame structure. Looks like we have a repeated training sequence to do the timing synchronization. And so as I mentioned, we have some on-off assignment. So basically, we try to assign the small pieces to some small slot. So this is the frame looks like after the on-off assignment. So this is quite interesting because no one is doing this. And we have a special designed timing synchronization algorithm. Basically, it's still doing it's still based on the cross correlation algorithm. So we have some peaks, so we know where the transmission starts. And we also using the Reed-Solomon code to do the channel coding because, as we said, there can be some readers at some no location due to our scheme because you are doing it randomly on and off. So it works pretty good. And so our main goal here is to try to see, since it's on off, we want to see how the transition looks like because we want to do the switching, switch it on and off very quickly. And this is our measurement. So when it's on, so you have a high level, and when you turn it off, you have a transition. So we see, okay, it's quiet enough, so we can receive very useful information. And we also measure the beta error rate for different scenarios. Basically, with this two setup, this is a benchmark, like you can have with cable. This is a over-the-air transmission. So basically, it's our first prototype of this new scheme, and we got very interesting results. Yep. So that's it. Thank you.